Ohm's law, we'll come across it more formally in a bit. V equals IR. So for a given voltage, so if this was fixed, we've got a given battery. The more this thing we call resistance is, the lower the current. So it's a bit of a stranglehold. The bigger resistance is, the lower the current. You can think of it as an inhibitor of current is really what we're getting at when we say resistance. It's there in the name. It's a resistance to current. As electrons carrying current move through a component, so the question now is, where does that come from? You know, why? Why does it have to be the case that there is resistance in wires? Why can't the world bend to our whims? And it's because of those blasted positive ions. So we've got our electrons, we've connected up our cell, hooray, hurrah. If I draw it this way around, the current, as a reminder, is going this way around, but that means the electrons are going this way around. Okay, my electrons are generally drifting from the left to the right. Cool, 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 cool. But they then collide with each other, but they also collide with the positive ion metal lattice. This is particularly the case because, well, positive and negative objects are attracted to each other. So it's almost inevitable. And as with any other collision, just because these are very small particles doesn't mean that the usual rules of collision aren't followed. They whack into each other and they impart kinetic energy. The kinetic energy of these microscopic particles is the phenomenon we call temperature. Okay, so these collisions produce heat. On the macroscopic level, temperature doesn't really exist. It's a purely macroscopic phenomenon. You can't talk about the temperature of an individual particle, for example. You can talk about its kinetic energy. And then as you zoom out, zoom out, zoom out, and you've got, trillions and trillions of these particles, and they're all jiggling about, that expresses itself at the scale of human beings as temperature. We touch it, it feels hot. That's because we can feel trillions and trillions of atoms bouncing against us and injuring ourselves and so on and so forth. As heat is produced, well, all the particles vibrate more, which makes it even harder for our poor electrons to try and get through. It's bad enough as an electron trying to sort of do a hurdler's sprint, trying to jump over and in and around all these obstacles. But if the obstacles themselves are moving and bumping into each other, it's going to get even harder. And so the current encounters some resistance, but then the current itself causes even more resistance as the temperature increases. So the resistance is a circuit component's opposition to electric current. Resistance is equal to the ratio of the potential difference across a component to the current flowing through it. Yep, that's true. So this is just a reworking of Ohm's law. So expressed mathematically that way, you could say, well, resistance, although qualitatively I can define it as, or think of it in my head in sort of friendly terms, I can think of it as something that impedes current. In mathematical terms, we're saying for a given current, for a given pace of electrons firing through a bit of metal, how much energy per unit charge is going to be lost. For some materials, the cost is very high. They're very resistive materials. For some materials, it's very low. Superconductors or whatever. In fact, there's no resistance at all in superconductors. We'll talk about that later as well. Very exciting. Resistance, one final thing, I can't believe I haven't mentioned it already, is measured in ohms.